All right. Good afternoon, class. Sorry I'm a little bit late getting started. I was finishing up my beans that I was eating for lunch. And also I had to shut Bugger up because he was barking at some kids walking on the sidewalk. So, today what we're going to do is we are going to talk about what is called RL circuits. What are called RL circuits. And an RL circuit is a circuit that is built up out of two things. Hello, Potato Master and AWOL. An RL circuit is made out of a resistor and an inductor. And we're going to assume that the circuit has some amount of current flowing in it at first. So I'll call that I naught. Hello, Alex A. So how does it have that current? Maybe there was a battery that was in the circuit, and then the battery was switched off or something like that. Okay, so it got the current started. Now, basically, like I said the other day, inductors don't like change in current. So generally speaking, if you shut the source of the current off, the current will just stop immediately. But because we have this inductor, the inductor doesn't like changes in current. And so it's going to keep the current going longer than it normally would. Okay? Knock it off, Bug. What the heck are you doing? All right. So we're imagining that this current is flowing in the circuit initially. So I'm going to label the positive side of each component. So the positive side is the upstream side. Hey, Aisha. Bug. He's being very naughty. So I'm labeling the positive side of all the different components and the negative side. So the positive side is the upstream side. Hey, Christian. So now I'm going to do a KVL loop around the circuit. Okay. So I'm going to start here and I'm going to go around in the counterclockwise sense. So first thing I do is I hit the positive terminal of the inductor. So I'm going to put or the voltage of an inductor. Then I continue through the inductor. And then I hit the positive terminal of the resistor. The voltage across the resistor is given by Ohm's law, which is I times R. And then it's only two things in the circuit, so that's it. So I would then set this equal to 0. Okay? So by doing some algebra, I can rearrange this to get di dt equals minus R over L times I. All right. So this is a simple differential equation that we're going to solve. And so the way you want to solve this differential equation is by separating variables, putting all the i's on one side and all the t's on the other side. So rearranging it, I get di over I, 1 over I di, I di 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 di, equals minus r over L times dt. All right, so I've separated the variables. So now what I want to do is I want to integrate both sides. So this, and on the time side, I'm integrating from 0 to time t. And at time 0, the amount of current is I naught. And then at time t, the amount of current, we'll just call it I. So doing the integral of di over I, that's a logarithmic integral. So we get natural log of I over I naught. Okay. Doing the integral on the right-hand side, it's just t is going to be the integral on the right-hand side. So we get negative r over L times t. So we can take this and we can solve for I quite easily. And we get that I of t is equal to I naught times e to the negative t over L over R. Okay. So you can see that we have an x. Now, one of the things I wanted to say is that, remember how I said if you didn't have the inductor, the current would go to 0 immediately? But since you have the inductor, the current still goes to 0 eventually, but it just takes more time. Okay, so the inductor keeps the current going longer than you might otherwise expect. You can see that the time is compared to L over R. So what that means is that the time constant is L over R. Okay, time constant for a RL circuit is different from the time constant for an RC circuit. Okay. So these are two important equations. We could also take this and we could solve for the voltage as a function of time. So voltage is the current going to 0. Okay. So you could see that when, I'm going to do a little sidebar calculation. When the time is equal to 1 time constant, you would have that the current is equal to I naught times e to the minus tau over tau. So you get I naught divided by e. So every time constant, the current is divided by e. E in the 2.7 e. So that means that it goes to about a third of its original value every time constant. Okay. So the voltage is L di dt. So we can take the derivative of this. We get L times the derivative is I naught times minus R over L times e to the minus t over L over R, which is equal to minus I naught times R e to the minus t over L over R. So this is the voltage as a function of time. We could also get the energy stored in the inductor as a function of time. So if you recall, the energy stored in the inductor is 1/2 L I squared. So we would have 1/2 times L times our I of t is I naught e to the minus t over tau. So that quantity squared. And so that would give us 1/2 L I naught squared times e to the negative 2t over tau. So this is the potential energy in the inductor as a function of time. Okay. So that's more or less the lesson today. I do want to say one additional factoid about inductors. So I'll say factoid. In a DC circuit, inductors are just wires. Why do I say that? Well, if you have an inductor, if you have a DC circuit, the current is a constant. So that means that di dt equals 0, okay? Which means that L times di dt is 0, which means that the voltage across the inductor is 0. The only time, so in a DC circuit, the inductors are pretty much useless, but they do, because at that moment, the current goes from 0 to its DC value, so the inductor is going to care about that. There's going to be a non-zero derivative of the current. Okay? So that's pretty much the lesson. I'll tell you a little story of something I saw yesterday or the other day when I was walking the dogs. I saw some like a gang of guys with mullets and tattoos. They were shirtless, so they had their mullets and their tattoos, and they were riding around on bicycles that had like motorized bicycles, not a motorcycle, but like a bicycle that you could get at Walmart or something with a motor attached to it, and they were riding around the neighborhood. And so it kind of reminded me of Mad Max a little bit, if you've ever seen the movie Mad Max. So I thought that was pretty funny. So maybe that's what the world is going to turn into if this goes on long enough. All right. So that's all I have for today. Enjoy the rest of your afternoon, and I will talk to you tomorrow.